Hey everybody, this is Larry. This is day 9 of the Leetcode Day Challenge. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this one. And of course, I'm going to do an extra problem after this, I think. So definitely check that out. Have to reset. But hope everyone's doing okay. It is almost Friday, or it is Friday, depending on when you're watching it or when I'm recording it. Though that part I should know. But yeah, so hit all the buttons and hope everyone's just doing okay with the weekend coming up. Another week, right? Yeah, a little bit of a health update. Nothing bad, I swear. Because I've been just talking about my health a little bit because that's just been what I've been interested in. This is a little bit of like a vlog, so maybe I could watch it in the future and be like, oh, Larry is an idiot that day. But anyway, I did get a continuous glucose monitor. So this thing, does that show up? This thing on my arm. So I could track my glucose level after I eat certain things. First thing I learned is that Korean food has a lot of sugar in random places, or maybe just eating out in general, but definitely the Korean place that I went to. So that's the problem with being old, is you have to make decisions about not eating as much, or not eating some things, because I'm still trying to bulk, so I'm going to eat a lot. Anyway, just a random update. Definitely, if you have any questions about that, let me know in the comments or come to Discord, and you could follow me as I kind of talk about that journey. I'm not a fitness YouTuber, but in case people are curious, because I was curious about all these things, and I was just looking it up a lot the last couple of days. Anyway, let's take a look at today's problem. Sorry for the intro. 368, largest divisible subset. Given a set of distinct positive integer numbers, return the largest subset answer such that every pair answer sub I, answer sub j of elements in the subset satisfies. Okay, cool. I mean, I think so. The first thing I would do is I would sort, right? Maybe if we need to, we could take it out if that's the issue in the complexity, but n log n is not an issue, and given that n is 1,000, not going to worry about it. And then now the reason why we do it this way is because then now, instead of having this like answers I, answer j thing, now you can have you can have it in one direction, right? Meaning that in this case, every num sub j is going to be greater than num sub I. So then that means that it has to be such that num sub j by num sub I is equal to 0, right? So that's the first thing we want to do. That's the thing of sorting. That's what sorting gives us, a structure that we can kind of exploit in this way, right? Right? Okay. And then the second thing is that what happens when you add a number to a set, right, or subset or whatever? Well, then now. Okay, yeah. So let's say you added a number, you have the number A to begin with, and then you added the number B, and of course, B is going to be greater than A, and that's how we define it, or I'll write it like this, right? In that how we sort it, and it doesn't really matter. But in this case, it's just in that order. And as we said before, we have B mod A is equal to 0. Well, now what happens if we try to add C, right? What happens to C? Well, C is going to be, in this case, I guess it could be equal to, I don't know if they are unique. So then this is going to be the case, right? And it so happens that now so this is still true, of course, but we already knew that, so we don't have to check for it for C. And then we also have C mod A is equal to 0 and C mod B is equal to 0, right? What does this mean, right? Well, C mod B is equal to 0 is the one that we have to check. Okay. So what do these two things mean, right, together? Well, C mod A is okay, fine, it's interesting, and C mod B is interesting together. But together, you only need to know this, because if C mod B is equal to 0, then this is always going to be true. And if this is true, then that means that the problem is that every pair is going to be mod 0. So then we only need to worry about this. I don't know if this identity, I don't even know if it's an identity really, but I don't know if this is well known, or if I need to kind of go over in detail. I'll go over it very briefly, but really, I mean, I think the thing that I would try to do in my head, maybe on paper, if especially if you're newer, is just play around with numbers, right? For example, if you have like 2, 4, 8, right? Then now you have 8 mod 4 is equal to 0, and then 8 mod 2 is equal to 0. Well, of course, because for mod 2 is equal to 0, the smaller part is always going to be true and the bigger part is true, right? Hope that kind of makes sense. I know that's not a proof. I'm not really good with proofs of these number theory. Like maybe could, I don't know, do some. I don't know, right? The proofs are kind of tricky for me. I'm not as well versed as to like these proofs with respect to proving it under the mod space, right, and stuff like that. But you can kind of see that. And then, but my point there then now is that okay, now instead of having 3 formulas we have to check, we just have to check one, and we only have to check one when we remove this number, right? So, oh sorry, when we add in C. So that means that we only need to do one check on this. So that's pretty much basically the idea. And from that we can kind of say that if you have a subset, then that subset is just going to be represented by the biggest number, right? Because the biggest number is the number. You assume that the biggest number already mods all the smaller numbers is equal to 0, or all the small numbers evenly divide into it, right? So in that case, then I guess I don't know why I have struggled with this, but yeah. So if B, I guess there is a easy proof. Hang on. I think I just didn't say it out loud, but yeah. But basically, you know, if B mod A is equal to 0, then that means that B is equal to K times A for some K, it doesn't matter what. So then here, yeah, so then you could say that this is mod K times A, and of course, if you do a multiple of A is equal to 0, then this is equal to be 0, 0. That's basically the idea. Anyway, about the representative number, if you have the biggest number, already implies that all the smaller numbers are already fitting into it, right? So that's basically going to be the thing. And from that, we can construct a dynamic programming solution with path reconstruction, right? And the dynamic program solution is because each state means that I'll try to do this top down because I think I think it's worth learning path reconstruction top down. But yeah, so let's just say we have, I don't know, get max, I don't know, it doesn't really matter, right? Index, right? And we have n is equal to length of nums. And then the idea here is get the max number starting from index, right? So then now, this means that this number is going to be the biggest number, right? So nums of index is the biggest number, maybe, right? Yeah, I think that's fine. You don't have to. I mean, you could. Yeah, we need to kick it off, but that's fine, right? If index. No, we don't even need a base case for this one, I think. Yeah, so best is equal to 1 for one number because you have this number as its own thing, right? And then now you just go forward. So for I in range from index plus 1 all the way to n, well, n minus 1 inclusive, we're going to, if num sub I mod num sub index, actually this is kind of, I'm just going to use j for is equal to 0, then now we could get max of j, right? So best, this is going to be this plus 1, and then we just, max it between this and that. That's one way to do it, right? And actually, I'm going to leave it like this so that we can talk about path reconstruction in another part. Usually I would probably just tie it in now, but yeah. And that's pretty much it. So then now we just loop brute force over which to start. So then you can just do like for I in range of n, best equal to max, best get max of I, and that's pretty much it. So that's the first one to start, right? So best is equal to 0, and yeah. I mean, this isn't the right answer yet because you have to return the output and not just the number, right? So yeah, but hopefully this so right now this is just brute force. There's no nothing. This is just brute force, and of course this branches a lot, so this is going to be exponential as we add in more numbers, and with more numbers and exponential, it is going to be very expensive. And you could actually kind of do that with, I guess, a variation of this, right? Just like 16, 32, 64, 128. Yeah, I guess I think this is actually still fast enough, to be honest. But let's see. Yeah, I guess this is still fast enough. Still got the answer though. But okay, fine. But like, it branches out. It's gonna be a little bit slow. So what are you gonna do, right? And what you're gonna do is, of course, dynamic programming. And here we look at, and the reason why we can do dynamic program, there are a couple, but is that for every input we get the same output, right? So yeah, for every input, there's no side effects. So for every input, we get the same output. So the idea, I mean, dynamic program memorization, the different way of saying it, and there are different ways of thinking about it. And sometimes I say it in a different way, so that maybe it triggers, you learning and thinking about it in a different way. But for this particular problem, maybe you could think about it as like, okay, well, if every input we get the same output, we just save it down. It doesn't even matter about like all these funky things about state. But then, for analysis, is that, okay, index could go from 0 to n, and each, so what's the total time, right? Well, total time is just, you go to time per input times number of inputs, and index, so number of inputs is just the number of index, so that's O of n, and each input takes O of n times, because there's an O of n loop inside, so this is going to be O of n squared time, if after we cache it, because otherwise this goes unbound, right? So yeah, so then now we add in the cache. Right. Yep. And I just like writing it like this, at least for learning purposes, because it's just very easy to read. You don't have to work, and very easy to figure out how many things you have to do. I know that there are other ways of writing it, and feel free to. Yeah. Yeah, still wrong because we haven't, but you can see all these things, and it matches the number count. Okay, so then now you go, okay, well, that's maybe useful, but is it? Right? So then how do we get the final answer, right? Well, I mean, there's, like I said, there are things you can say about path reconstruction and all these things. They're fancy terms, but for this one, we can think about it a little bit easier, right? We just kind of keep track of, well, what's the best move that we can make at every thing, and then we just keep track of it. So then best move is, you go to let's go none times n, and then here, yeah, so here maybe we could write best move of index is equal to, I guess actually I should put it here. I guess it's just none otherwise, right? So here, that means that now we write something like, if get max, so R is just the return value, get max of j plus 1. If R is greater than best, then best is equal to R, right? So this is the same code as before, but now we also want to keep track of this, so then maybe best move of index is equal to R. Oh, sorry, not equal to R, equal to J, right? So we keep track of it, and we update it so that best move of index gets you the best next move. And that's basically all the change you need to kind of set it up, right? Because then now here, and we have to write this a little bit different as well. But yeah, same thing, get is I, right? So if R is greater than best, then you have this best is equal to R, right? But then now, yeah, and then maybe you could write just best start is equal to none, and then best start is equal to I, right? So then now we know what is the best index to start from, and then now here we just walk the thing to the best moves, right? So here maybe I'm going to write this a little bit sloppy and lazy, to be honest, and you could do this in an iterative move, but I'm just going to do it recursively because it kind of matches the structure of everything else, right? Get best move of index, right? So then here, or get next best move maybe. I think maybe best move is fine, right? So then now we go yeah, if best move from index is not none, then we get best. So then the next move is you go to best move of index, right? We want to append it to the answer, and then we want to go visit it. And that's pretty much it. And then now we can just return answer. I mean, you still have to call the function. Oops. From best start. And that should be good. Okay, is what I want to say, but it's not. Huh. Dong dong dong. What did I do? Why am I short a little bit? Oh, I'm returning to. I append the index and not the. Well, that's one. So we only. Why am I? And I'm appending the next move instead of the current move, so that's a little bit silly. I don't know. I'm just really sloppy today. Okay. Yeah, we don't care about next. I don't know. Just really not thinking. Okay, so there you go, and we'll give it a nice submit. And yeah, I've done this other ways before in the past, probably iteratively. Yeah, I probably did it this way. So I just wanted to kind of, show that you can do things multiple ways. And this time I did it tops down, and did it the same dynamic programming way that we did before, and without all the really funky things about path reconstruction. You can just see that, hey, look, we want to say what our best move is, and then at the end we want to, well, just walk the path that you took, right? So yeah, that's pretty much what I have for this one. Let me know what you think. This is going to be n squared, like we said, and of course this is O of n because we just kind of move, you're moving forward. There's only at most n of them, so that's going to be O of n, and of course O of n space because of the answer and also the caching. So yeah, that's pretty much it. Let me know what you think. Stay good, stay healthy, to good mental health. I'll see y'all later and take care. Bye bye. Let me show you actually. Okay, the top and then the bottom. All right. Stay cool, everybody. Bye bye.